Hi, everyone. So today we're very happy to have Cesar give the first seminar of the semester before the beginning of the semester. And the topic of his talk is going to be on some aspects of the N-partite information in conformal field theories. Thank you so much, and please, Cesar.
Okay, Kenima, thank you very much for the invitation and the opportunity to speak today. Yes, as the title said, I will be talking about some particular results regarding the N-partite information in conformal field theories. So let me start with a brief motivation. The motivation of this work is essentially coming from this Weinman Reconstruction theorem, and is the idea that, at least in the context of axiomatic QFT, that essentially having the information of all the correlators in a particular theory is equivalent to knowing the theory. So you can write everything in terms of this data, let's say. And this data, of course, has to satisfy a lot of self-consistency constraints. So the idea of this theorem, or the motivation for this theorem, is because we wonder whether something similar will happen also in terms of entanglement entropy quantities. So is there a possibility to actually have a full description of a QFT if we know all the entanglement entropies for any type of regions, for instance, in particular for the ground state of that particular theory? We know that the entanglement entropies are not actually well defined in QFT. So maybe the question will be if we know all the mutual informations for all set of regions. In this case, the regions are really the causal completions of the space-like regions. And just by adopting this perspective, since we have here n correlators of n objects, so maybe n operators, so maybe you can, by taking the mutual information, consider also the n-partite information, which is precisely the object that I would like to talk today about. So this is the general motivation. So let me start then by doing a quick review of what the n-partite information is.
Can I ask you a quick question? In the previous slide, so this idea, is this idea that this entanglement reconstruction motivated by finite quantum systems? Because I suspect that it won't hold for, like you say, tri-partite 3 qubits. If you give me the entanglement entropy of 3 qubits for all the subsystems, I wouldn't be able to reconstruct anything. I wouldn't be able to construct much, right? Am I wrong?
Okay, no, I think it's correct. I mean, yes, this is true. No, I think this is in the context of field theory. So we'll be just in this continuous regime, infinitely many degrees of freedom. This might be possible. At least philosophically, this is a valid question. Let's say, yeah.
Thank you.
I agree. Okay. So the n-partite information then is just defined in terms of combinations of entanglement entropies. This is the general formula. So let me work out a little bit better this formula in some detail. So in detail would be like this. So you consider first all the individual regions, so a set of n regions. So you consider the entropies, the von Neumann entropies of all the individual regions. And then you start changing signs and considering like all the pairs of regions that you can form out of the n, and so on until you get to the set of all the regions, individual regions. So, and this quantity satisfies some simple properties. First of all, because of this alternate signs, then all the area terms, the divergences that comes from the entanglement entropies will cancel, which render this quantity well defined. Second, since we are interested in computing this thing for the ground state of CFT, then it should satisfy Lorentz invariance, conformal invariance. And third, just from the definition, you can also have a recursive expression for the n-partite information, which essentially, in terms of the n-1 partite entropy, which essentially like probes essentially the extensivity of the in-1, the n-1 partite entropy. And finally, we have clustering. So because of the way these things appears in the formula, then if you divide the n regions in two sets, like this set and this set, and you put them far away, then you will get that the n-partite information will decay or will go to 0. Quick question: did you see my cursor?
Yes.
Okay, because I will try to point at things.
Actually, okay. Another question. Sorry.
Sure. Of course. Go ahead.
So, what do you mean by saying that it's Lorentz and conformal invariant?
It's just that for any region that is connected by a Lorentz transformation of conformal transformation, any set of regions that are related by a global conformal transformation or a Lorentz transformation, the N-partite information is the same in the ground state.
Yeah, so you're saying that your vacuum state is Lorentz invariant conformal. You're looking at the vacuum.
Yes.
I see.
Yes. We will consider that. Yes, exactly. Yes, this is just for the type of quantities and the theory. Yes, for a particular state, this is true. Is all I'm saying. Yeah, exactly.
Also, am I right that there is no relative entropy version of this?
I mean, in principle, just because of this recursivity, you could in principle just go all the way to the mutual information and write things in terms of relative entropies, let's say,
Of touching
by these recursive relations. But it's not like directly, there is as far as I know, there is not a direct relative entropy expression that immediately gives you the N-partite entropy, the N-partite information.
No, I meant something else. I meant that all the terms in this expression, do they involve disjoint regions or they're also involve touching regions? So if they're disjoint, you're saying?
I see. No, in my case, I'm considering that the original set is a set of disjoint regions, but each piece can be made of other disjoint regions or touching regions, or it can be as complicated as you imagine. But all the set itself, at least for me, doesn't have any touching. Yeah. The N set. Okay. So just to give an example that is very famous and extremely important is that the mutual information is just one particular case of this family of N family generalization. So we all know the formula, the explicit formula. And of course, it obeys all the properties that I have mentioned before, but it also has some extra properties that make it actually an extremely interesting quantity to study. So first, it's positive definite. And this immediately tells us something about the entropy, is that the entropy is subadditive or subextensive, if you want. And the second is that it's monotonous. This is one of the hardest properties to satisfy and why the mutual information is so interesting as well. And finally, it has this nice connection with norm-bound, with the connected correlator of norm-bound operators. So it puts a bound on this type of correlators. So it's a nice measure of the total amount of correlations between two subsystems, let's say. So all these properties are special to the mutual information, and so this is very important. The other quantity that is also interesting, of course, is the tri-partite information. The formula is, as I said before, just applying the general formula, you get this, and it satisfies all the properties that I have mentioned. In particular, it proves the extensivity of the mutual information. So let me write it explicitly. So and this is this recursive relation. So the tri-partite information can be written in terms of two-partite informations. And in particular, this quantity has been of some interest in holographic context, for instance, because we know that holographic system satisfies monogamy. At least by that, I mean the leading piece in large N expansion is negative for geometric states or holographic states. And another aspect that also comes from considering this quantity is this model that you get when you impose this equality. So a strict extensivity in a CFT. If you impose that the CFT is extensive, so that means that given any triple of regions, you get the I3 equal to 0. Then Cassini and Huerta showed that actually the mutual information is completely fixed. So it's just a concrete formula, geometric formula given in terms of this correlator, where the correlator that appear here is just the correlator of a conserved current, spin one current. So this is completely fixed. And so this is very interesting, has been studied and in many contexts, and in particular recently in a work with Pablo Wen and Horacio Cassini, we proved that actually this model is only physical for d equal to 2, where it corresponds to a free fermion. But for larger dimensions, there is no CFT which has this mutual information, roughly speaking. Okay, so this is a motivation for these two particular types of N-partite information, but you can consider N generalizations and see how you can do some progress in this direction, like just considering this type of quantities in conformal field theories.
Sorry,
yes, sure, go ahead.
How would you say, what is the physics of this I3 equals 0? How would you describe how is this a constraint, in what form?
I mean, it constrains, I mean, this is a very strong constraint because basically you're saying that the mutual information is extensive. So that means that the mutual information of the union of two regions is just the sum of the mutual informations. I don't know how much physical information is there in this statement, but I believe Bartek has some physical intuition that imposing this condition is equivalent to saying that all the entanglement can be interpreted in terms of EPR pairs, essentially. So like all the entanglement between this larger system and a smaller one is just a sum because it's made out of EPR pairs. And this is a very strong physical condition. If this is true, it's not completely clear that this is true, that imposing I3 equal to 0 means only EPR-like entanglement. But if this is the case, then it is understandable why there is no physical models with this property, let's say.
And also, what principle causes the clash with the existence of such model in D larger than 2?
I mean, essentially, I can answer this a little bit better whenever I write down some explicit formulas. So essentially, there are some formulas for the mutual information that this formula does not satisfy.
Thank you.
And that you can derive using replicas, trig, and things like that. So, and that's precisely where I'm going towards. I mean, this is the direction I'm going to, let's say. So, but before getting to these general formulas, let me just review some generalities. So for computing these quantities, we're going to use the replica trick, in which what we compute actually is just the running entropies and take the n going to one limit. And the running entropies is just these traces of integer powers of the reduced density operator. And so we have these two alternative ways of interpreting this quantity, the trace of rho to the n. One is this in terms of Euclidean path integrals, where we do some cyclic identification and we rotate along the boundary of the region in question, and then you go from one sheet to the next, and you construct this type of Riemann surface. Or you could also do the same in the space of operators. The space of operators, you can just do the identification when across the t equals 0 slice for operators that are in region A and do nothing in operators that are in A bar. So, and the object that do this identification is what is usually called the twist operator. I'm going to use this letter for that object. And so from this perspective, what we're going to do is to study this object, because that's like the basic object that allows us to compute the rings. But I'm telling you everything about the entanglement entropy, but just using the formulas that I described for you, you can compute things like the mutual information or the N-partite information just by taking combinations of entropies. So for instance, in terms of this twist operator, the mutual information will have this structure. It will be the correlator of these two twist operators divided by these individual twist operators. Because of that, then it turns out to be natural to separate the twist operator into a piece that is proportional to the identity and everything else. So we will most of the time be referring to this tilde twist operator, which is just this part, let's say the non-trivial part of the twist. And if you do this replacement, then what you get is just the log of 1 plus a correlator. So that means that when taking the n going to one limit in order to get the entropies, or in this case, the mutual information, then you actually get a quite simple formula. You just get that the mutual information is given by the limit of the correlation function of two twist operators, one for region A and one for region B. Okay, so this comes just complete generality, and I have made no assumptions up to this point. And it turns out that this formula actually generalizes for an arbitrary number of regions. So the N-partite information, you can compute it just by computing this correlator of n twist operators. And this is the thing that we're going to do. This formula can actually be proved by induction using this recursive relation between the in and in minus 1. But we are not going to do the proof here. Okay. So let me say a little bit more about this, because in general, this object is very complicated. So in particular, Cardi in this paper, 2013, shows us that in the case in which you consider regions that are far away from each other, like where all the regions are separated from each other for a large amount compared to the characteristic size of the regions, then you can think of this operator like a semi-local operator, or you can just write some kind of OP expansion in terms of a complete basis of operators in this replica CFT. So it's n copies of the CFT. So let me elaborate a little bit more on this. For example, in this expansion, then you can imagine that this twist you can write down explicitly the contributions to the twist operator coming from a particular primary of these NCFTs. And then this will have this structure. So in principle, you can have just single operators in a given copy of the CFT. This index I is just labeling the copies of the CFTs. So you can have things that goes like linear in the single copy, or sums of single copy operators, sums of double copy operators, and so on, an arbitrary number of copy operators. And also you can have derivatives and all possible, essentially just derivatives and other matrix. Depending on the index structure, you can get other more complicated structures here. But nevertheless, just because we are just dealing with a single correlator, then it's very easy to notice the following. If we assume that this operator is dominated by a single primary operator, then you know how this scales with the distance. So an n correlator of n primary operators will just go like 1 over the distance, like the typical distance between operators, to the sum of the scaling dimensions of each of these operators. So this means that in this long distance regime, then you just need to keep the lowest dimension scaling operator in your CFT, in your n replica CFT. And this is exactly what we are going to do. So, so based on these generic observations, the lowest scaling dimension will be this, but you can argue that the coefficients will go to 0 and will not contribute to the N-partite information due to this limit. And then the next lowest scaling operator that appear in this expression will have this form. So this means that at long distances, it is a good approximation to just keep the contribution to the twist operator that come from two operators in two different replicas. So this is then the conclusion of this list. So but now let me just make a parallel between this type of correlators and just ordinary CFT correlators. And this is what I do here. So here we have a correlator of n-point correlator, let's say, and now we are considering just an n-partite information, which looks like an n, also an n correlator, but the n correlator is roughly like is made out of two operators. It's like roughly like the normal ordering of the square of an operator, roughly speaking. There are some index here that you have to add up, but you can already get some intuition of what to get just from this intuitive approximation.
Sorry,
so yes, go ahead.
Can I ask a silly question? I'm just confused
Sure.
about this. In the replica CFT, there is no OP for OI, OJ?
Yes, this is the OP precisely. The coefficient that appear here will be the OP of this twist operator in OI, OJ.
No, I'm asking that why can't you write down an operator product expansion for OI, OJ, and then simplify this and write everything as a sum, an infinite sum over just one single operator?
Oh, no, because precisely what you have here, I mean, when you introduce the twist operator, what you have is just n decoupled CFTs. So there are no OP between OI, OJ. These are just decoupled CFTs. There are no OPs, yeah.
Yeah, okay, thank you.
Okay, perfect, thanks.
Actually, this OI, OJ is sort of like a composite primary of this theory.
Yes. The CFT is a composite primary, yes. But,
okay. Thank you.
Yes, perfect. Okay, so but then this is just like just to get some intuition of what type of formulas you will get, no? But then if I do this approximation, which is basically just O square, then you will immediately get the right scaling behavior. So the endpoint function then of the n-partite information will scale like the distance to the 2n delta, where delta is the lowest scaling dimension in my theory. I'm making also the assumption that the lowest scaling dimension in my theory is a scalar operator. You can do this with other type of operators as well. But many formulas will depend on the fact that it's a scalar. Okay, so roughly speaking, seems like the n-partite information also looks like a correlator. However, this is in odds with this clustering property that I was mentioning at the beginning. So while an ordinary correlator factorizes when you took a subset of points and you separate it from the rest, the n-partite information does not factorize. It should go to 0. So this thing should not hold. So a simple solution is that actually the n-partite information will look like this, but for connected. We'll have only connected contributions of this type of correlators. And in that case, you satisfy clustering. So I'm just guessing the answer for this quantity that I'm telling you that I'm interested in computing in this particular region. Okay, so now let me go back to the original motivation, because after having gone over all these ideas, I think now it is more clear, the motivation. So in particular, in CFTs, then this idea of reconstruction essentially means that you will like to get a way to get the scaling dimensions, the spins of all the primary operators, as well as the OP coefficients, because this in flat space basically characterizes or defines completely my CFT. And somebody hands you a set of correlators, endpoint correlators satisfying all the self-consistency properties, then you can get that information just by looking at 2-point functions of primaries and 3-point functions, because from this you get the OPEs, and from this you get the scaling dimensions. And of course, the other higher order correlators will be important because you will want to make sure that they satisfy the, for example, the crossing symmetry and other constraints that this correlator should satisfy. So of course, there should be a set of consistency conditions on these higher order correlators. So in parallel, basically what I'm going to show you at the end, but here I would like to present you already the results in case I don't have enough time to go over everything. So the results of various computations is that the N-partite information actually has a similar structure like this one. No? So the mutual information goes like the square of the 2-point function at leading order. The 3-partite information actually already includes some OPE coefficients. So it has a term that goes like the square of the 3-point function, and also some terms that are just products of 2-point functions. And the coefficients that appear in front, we were able to compute it exactly. So we have formulas for this, for all these coefficients. I will talk about this a little bit later. And the new computation that we haven't presented yet is the similar formula for the 4-partite information. And as you can see, all these formulas are actually, you can just put the connected piece, and because they are all connected correlators essentially. You can translate into connected correlators. And this is kind of, I mean, this is already expected that you should get connected functions. So each of these contributions had the right clustering behavior. And we only get 3 coefficients for the I4, 2 for the I3, and so on. So this is the general formulas that we got already at this point. And now I would like to mention a little bit more about each of these formulas. In particular, notice that the information that we are getting is quite limited compared to the correlation functions, because here we are just getting the information about the lowest dimension operator. So, and of course, in order to make this reconstruction, we will need to have access to all the scaling dimensions, all the OPEs, and so on. But then the idea is that, of course, we are only getting this limited information because we are only keeping the leading term in this complicated expansion. If we work to keep all the subleading terms, then we will be able to systematically extract all the CFT data from these formulas. And that's just like a explicit realization of the motivation. But let me say some words about the mutual information, because okay, this is the general formula. The coefficient that appeared here was already computed back in 29. And we also computed in 2-dimensional CFTs, and we computed this work with Faulkner in the case of general dimensional CFTs. Just to see the explicit scaling with the radius and the distance, this goes like this. And these authors actually tell you something very concrete about how to think of the full expansion in terms of operators. So actually, they argue that the expansion has a very, very concrete form. It is given in terms of the conformal blocks associated to intermediate replica operators. So the mutual information for spheres that already resum all the contributions from each replica operator and all these descendants, it organizes themselves into an infinite sum in which it includes all the operators that can be defined in the replica theory, let's say. So in particular, this leading term will, as I said at the beginning, actually comes from an O-squared-like operator. But many operators cannot only be defined in this replica theory. So for example, you will also get operators like this, like you need 2 copies of the same operator, but you can get things that in a single CFT will not exist because this will just cancel. So you will need multi-copy CFT to define all these type of operators, and that make this expansion to be in general or in practice a little bit difficult to manipulate. It is type of expansion or this formula, the kind of formula that we studied, for example, for the EMI model that I described at the beginning. So by computing the different contributions that you would expect for the mutual information, you end up getting to some contradictions by studying this formula, for instance, to answer the question asked by Nima.
Sorry, a quick question.
Yes, go ahead.
Why are there no terms for OI or J? O1, O2?
Yes. Those are there. OIJ, arbitrary number of indices. That's what makes this very complicated. And the good thing is that it is kind of organized because you go from lowest to higher scaling dimensions. So there's a way of organizing, but once you go a few steps high in the scaling dimension, then you will get an explosion of replica operators. You get many replica operators.
Yeah, the reason I said that is that supposedly, at least in 2 dimensions, these type of O1 del mu O2s, these del mu's could be eaten in a upgrading B into a differential operator.
Oh,
Right?
can you say that? Because
So if you just, these del mu's, you could eat them in B and upgrade B into a differential operator, right? And then talk only in terms of the primaries OI, O1, O2, O3, blah, blah, blah. Supposedly.
Okay.
I mean, because
I see. The OP coefficient, you mean this type of OP coefficient, you can absorb it in the definition of
At least in 2D, we could do this explicitly.
Okay. That would be nice, actually. I mean, I think this formula hasn't been explored much. After this, there are very few papers that actually explore this. One of those papers is our paper with Horacio and Paulo. But I think there is some potential to understand this, at least, as you said, in 2D CFT, actually carry out the sum maybe explicitly in some theories and check whether this is true or not. Especially because the twist operator is you may be able to actually do explicit computations, like for the compact scalar, there are explicit computations for the Rennies. So maybe you can actually put this formula into test.
I see. Thank you.
In 2D CFT.
I guess maybe I should ask it a little bit differently. So here,
yeah,
like
sure.
delta bar, you meant these are global primaries.
Okay.
Is that right? Are these global primaries?
Yes.
I see.
What's okay?
As opposed to Virasoro.
Oh, I see.
So I mean, del mu of O is a primary. It's not a primary. It's like a global thing. Anyway, it doesn't matter.
Okay. Yeah. Okay. Yes. To me, I think those are global primary, but I need to understand better the distinction. Okay. So this is the thing that you can. I mean, how you can go away from just keeping the leading term. For the rest of the talk, I'm just going to be keeping the leading term, but I'm just telling you that there is a story that actually incorporate all the contributions of the subleading things. And in particular, this expansion is potentially so powerful that it might be enough to actually carry out this reconstruction idea. So actually being able to extract all the CFT data from just the mutual information of 2 spheres, for instance, disjoint spheres. But in principle, I mean, this hasn't been proved, so maybe you need to take more than 2 spheres, and for that, the N-partite information might be of interest to complete the program. Let's say if that inversion is not possible. So in particular, we studied the tri-partite information in this paper with Horacio and Paulo, and we got, as I said before, this explicit formula that, when written directly in terms of the radius and the distance, just to simplify the formulas, I assume that the distances are the same between all the 3 different spheres. Then you get this coefficient, and it is interesting that the coefficient doesn't have a definite sign. Of course, the N-partite information, as opposed to the mutual information, can have either sign, depending on the theory. Nevertheless, okay, and these coefficients are explicit functions that you can compute, and if I have time, I will tell you how to do these computations. But the interesting thing is that if we go back to the holography and this idea that for holographic theories you have monogamy, you may wonder what will happen for holographic theories. First, if you assume this generalized free field, then the OP coefficient appearing here will be 0, at least in order in large N. And then what you will get is actually that the I3 is positive, so the opposite of being monogamous. So this will immediately tell you that in holography, the tri-partite information at low distances, it will be positive. And it seems that this seems to be true, at least for free theories or generalized free theories. We went only to I4. And if you insist for an arbitrary theory, if you insist on having monogamy, then this will impose a strong constraint on the OP coefficient. So it will have to be larger than a certain amount that is larger than 2, for instance, for arbitrary delta. So this seems to be a very strong condition for these theories. We do not know any example of a theory that satisfies this. And going back to this extensive model that I mentioned quite briefly from Casina and Huerta, we could already see why imposing I3 is such a restrictive condition. Because if I force the I3 to be 0, then at each order in this large distance expansion, you will have to make sure that all the coefficients vanishes. And this means, for example, that at least this already imposes a strong condition on the OP. The OP has to identically be equal to this. So you could imagine that going to higher orders, then essentially this will fix most, if not all, the OPE coefficients. And that is not surprising that you can actually write down a closed formula, because essentially we'll be telling you that this will fix completely the theory, imposing such a strong condition in the CFT. Okay, so let me go back to the general formula, and I already basically presented the main results, but now I would also like to give some details of the computations that we have to go to getting those results. So to summarize, the kind of thing that we are computing is just an n correlator of n twist operators, something like this, in the limit when n goes to 1. So we have to take this limit. And we are taking the approximation which each twist operator is just given by this, when the O is the lowest scaling dimension operator of my theory. So plugging this into this formula, we'll have to analyze a correlator of this type. We have to consider sums of these twist OPEs and products of them. So this is a complicated formula, and I would like to tell you how to carry out this computation. So before that, I would like to pause a little bit and see if there are any questions about the rest.
No, I have a question with respect to the original motivation. I thought you said you wanted to reconstruct the whole theory from this mutual information in the same way as the Weinman functions, but you are not looking at that, or you're just looking at computing these INs, or?
Yes, I mean, because yeah, this is like a first steps towards this bigger goal, let's say. So first we have to have as much data as possible, and then we would like to see how this data can be inverted to actually show an explicit reconstruction. So yes, but then there are two things. One, in principle, you may, as I said before, you may be able to do it just with mutual information. But the thing is that since the mutual information, because of the reasons I just mentioned, it becomes very complicated when you go to higher orders. Maybe one possibility to complete this task is to consider N-partite information for various regions. For simplicity, we can do computations for spheres. Everything can be done explicitly. But,
no, but the objective will be like, if you know that, then you can know, for example, all the conformal weights and all the OPE coefficients of all the operators or things like that. Because here you only have this twist operator. The delta is only for the.
Yes. I agree. That's why this is like a very preliminary step, towards this direction. So one step which might be more fruitful is to understand the mutual information, because we have this general formula already. But computing the coefficients and this dependence with the conformal dimensions and the OPs is the hard part, let's say. So this is the part that we would like to understand better. So this is one direction, just computing the mutual information. Another direction that I'm trying to motivate is that we could also just consider not just mutual information, but tri-partite informations and other more non-local observables, let's say, things that depends on more regions. For instance, let me just close this a little bit before moving forward, because at leading order, the mutual information do not have any information about OPE coefficient. This is the leading order term. It only contains something that depends on the scaling dimension of the operator, this function here. And you can see that already by the fall-off. So the fall-off of the function will tell you the scaling dimension or the lowest scaling dimension operator. If you keep only the first term, that's what you get. Of course, if you keep the next term, then you will learn more about the other operators in my theory. But this will be a little bit like you might get entangled with other operators that comes from the replicas, like taking derivatives and so on. Now, already the leading term in the tri-partite information is telling us some dynamical information. For instance, they are telling you the OP. So in that sense, this might be complementary. Like you can study the mutual, but also the tri-partite and maybe other higher partite quantities. The thing is that the leading term is easy, and maybe with few sub-leading terms, you can get more information by considering multiple n's than just keeping a single I2. That's kind of the philosophy. I don't know if this is more clear now.
Yeah, thank you.
Okay, thanks. Quick question. The condition for the vanishing of I3 is not known in quantum mechanics, is that right?
Is known in, I think this, when does it happen? I mean, one particular case is for EPR entanglement, it will immediately have A3 equals 0. You said that in quantum mechanical system, this condition has a name or something.
No, I said it's not known. The necessary and sufficient. This is
okay.
not known in quantum mechanics. Is that right?
As far as I know, no. Yes, I really don't know the answer to that question. Yeah.
And another thing is that, I mean, this is a very ambitious conjecture to say that visual information, these N-partite information contains all the information. Maybe a simpler version of this or a looser version of it is more answerable. So instead of taking the limit of n going to 1, let's just keep the correlators of the n twist. Does that have a better answer? I would think that would actually uniquely fix that. Now, whether the limit of n going to 1 involves some information loss, I'm not sure.
I see. I mean, in some cases, actually taking that limit, it simplifies things.
But it's definitely more information.
Yeah.
But
at the same time, like when you take the n going to 1 limit, it's like you have to consider contributions from arbitrary large n that contributes to that limit.
Correct.
And that makes it also more complicated.
Correct.
So yes, maybe you can set up the equation just conceptually without doing any computations at the level of the Rennies. Maybe that's more doable, because it's like in the same sense that when you take the Rennies, then you can reconstruct all the eigenvalues of the reduced density matrix.
Yeah.
While with the entanglement entropy, you cannot.
I mean, I guess another way of posing this question is a question that we've been chasing for a while now, which is, what is the information theoretic quantity that is equal to an OP coefficient, right? If you can write that down in terms of correlators or twist, then you sort of have answered the simpler version of this. But anyway, yeah.
I agree. What is the information? Yes, I agree. That would be another way of, like, another direction. Maybe you have to consider another quantity, but yeah. Okay, thank you. Okay, so now I will move more.
Cesar?
Yes, go ahead.
Yes, sorry to interrupt. I have a question, mostly because of the confusion. So
Sure.
You said that when you have only EPR pairs, then I3 is 0. But I think we used to think that in holography there is only bipartite entanglement. But we knew that in holography I3 is negative. So doesn't that EPR pairs it's also like bipartite entanglement?
I don't think that's true. Why you said that in holography we have only bipartite entanglement?
No, but I think we used to think that, like, there was a conjecture.
Yeah, but I think that conjecture has been disproved. So
Actually, Matt Hedrick would argue with that.
Yeah. I mean, Matt Hedrick posed the conjecture, and then some group essentially argued that that's not possible. That's not consistent.
Right, but just the fact that I3 is negative in holography, wouldn't that just mean that conjecture is wrong?
That the conjecture is true? No.
No, conjecture is wrong.
Okay. No, but the point is that this what I'm saying is not true either. Like the tripartite entropy being 0 implies only EPR like entanglement. It's like and the other thing is that this is just also another conjecture. So we cannot prove a conjecture with another conjecture. Let's say it like that.
Okay.
This is
all right. Thanks.
Yeah. The other thing that I didn't mention is that in holography there is also this perfect tensor like entanglement, which was actually important for what Matt and company said. So they said, like, they're only like bipartite entanglement and four-partite entanglement in the form of perfect tensors. So this is something extra. So this perfect tensors, I think is involved in the fact that the I3 is not 0. This perfect tensor thing, it's not EPR.
I see. Okay, thank you.
Okay, perfect. Okay, so this is the organization for the most technical part of the talk. So maybe we have to skip over some parts. So first, I would like to show you some diagrammatic way of understanding the computations of the IN. Then I will tell you that at least for d = 3, we were able to check our results against the lattice. And then I might be able to tell you about the explicit form of the OP coefficient So we were able to get some formulas for that, how to do certain sums, and finally, I will end with some words about holography. Okay, so let me start with the diagrammatic, because I think this is kind of nice, although it might be well known by many of you. So for computing the mutual information, then as I said, we need to compute this correlator. Just let us start by showing you this method, the examples. And as I said, we replace the twist operator by this thing, which essentially is labeled by two indices. So what I propose is to represent this twist operator in the form of a line, where the labels on the line will describe the region, whose twist operator we are computing, and the endpoints will describe the copies or the replicas of the CFT. So here we have two replicas, a twist operator that has support on two replicas, and that describe the region A. So this is the type of diagram that I'm going to consider. So if I plug in this formula into this, then I get something like this. So these double sums of 4-point function in principle. So let me rewrite it here just for simplicity, and I will do this for the other contributions. And the next thing is that in order to carry out this sum, then the natural way of organizing is by considering contributions that only involve two indices, then contributions that involve three indices, and so on. So we organize this multiple sum in terms of the number of different indices that intervene. So for instance, if I consider n equal 2, this means that we are going to put only two indices in the formula. But graphically, that means that I need to put two twist operators in two indices, then we have to put it one on top of the other. That's the only way that we can put those twist operators. And for each line, then what we have is a power of Cij, so we have a square of Cij. We have two indices, and all the indices are ordered, so this index will be ordered. And the other piece of the information that I haven't told is that on each index, the number of lines will tell us the order of the correlator. So here we have a 2-point function in the index I, and another 2-point function in the index J. So this thing translates into this formula. And we will do this multiple times, so you will get used to this type of analysis. So this means that the mutual information will contain this contribution, which is actually the contribution that I told you at the beginning, where the coefficient that appears here is just the object that appears here. I will say a little bit more about the coefficient. But then you may wonder what happened with n equal 3. Can we do also this for n equal 3? Okay, yes, we can repeat the same idea, but the thing that we get is that now there will be indices that are connected only with a single line, which means that we have only the expectation value of a single operator, and we assume in the backend that these are 0. So actually, the only contribution will be this contribution to the mutual information. And so in general, then we will have the formula that I already told you, where the coefficient, whose formula I showed you before, is given by doing this sum. So we have to sum the square of the OP coefficients, ordered, and taking the limit when n goes to 1. So this is the definition. Okay, so we are done. We already computed the mutual information. We just need to now to worry about this coefficient, but I will do it later. So let me go quickly over the other partite entropies to see what kind of subtleties appears. So for the tri-partite information, you do the same. You plug in this formula into the general formula, and then you also explore what happened with n equal 2. The same story happened. Now we have to put 3 twist operators between two indices. You get this formula. Now you get like correlators of 3 operators, like the 3-point functions for in each vertex, I and J, and you do everything the same. And indeed, the coefficient that appears here is essentially this. It gives rise to the same function than before, where you only need to replace 2 by 3, and you get already the coefficient. And this will happen for any other N-partite entropy. So the thing that goes like the square of the correlation function, the coefficient in front, it can be computed already. It's just given by this function, essentially. But for the tri-partite information, the story doesn't end here. We also get this type of contribution. So now we go to 3 indices, and then we have to do the same story, put 3 twist operators connecting 3 indices, and it turns out that the only way that you get a non-zero answer is by doing this triangle. And the first subtlety that appears here is that now you have many ways of labeling this triangle, which are not equivalent because the indices are ordered. So we have I less than J less than Chi. And then that gives rise to this extra factor. So there will be symmetry factors in the same way that in standard Feynman diagrams. And we get, and this contribution will go like a product of 2-point functions. Each 2-point function corresponding to each vertex. So simplifying this formula, it gets to this formula. where once again, the coefficient that appear here is just this, the coefficient that appear in the tripartite information. And I'm just claiming that you can carry out this sum explicitly and get a explicit function for that coefficient. It also depends only on the scaling dimension of the operator. There are no more dynamical data. And the thing I already told you, this gives rise to this nice formula in which the 3-point function squared is what gives us this OPE coefficient, and everything I said before, it applies for this formula. Okay, so to complete, let me go to the next case in difficulty, which is the I4, just because some things becomes a little bit non-trivial, but the process is already there, so maybe I don't have to say too much more about that. So we just plug in these twist operators and we start exploring the situation for different orders, for different number of labels. So we have the n equal 2 is exactly the same than before. We get the square of the 4-point function and a coefficient that is already known. Now for n equal 3, we get many different plots, many different graphs, let's say. All of these are like topologically related. But then now we have 3 indices and we have to put 4 lines, 4 twist operators. So we can do it in 12 different ways for each of these graphs. And then each of these graphs will contribute to the coefficient in this form, where the powers Cij just corresponds to the number of lines connecting I and j indices, for example, for this, and so on for the other ones. So now the coefficient becomes a little bit more complicated. The functioning form is very easy to see, just a 3-point is 2 3-point functions, because we have 3 lines here, and 1 2-point function. So this is the type of terms that will appear here. And this is the coefficient. So the number of terms is just, once again, the number of different ways you can label these lines, or different ways you can put the twist operators, let's say. Another contribution of n equal 3 is very similar, but now what it will appear is a 4-point function and a product of two 2-point functions. And all the plots that are related, the coefficients will appear here. I'm ordering the indices, and this is the function, the explicit function, where the coefficient is obtained from this, and you get 2-point function, 4-point function, and so on. Now there will be also more graphs when we go to 4 indices. So just quickly, just by looking at drawings. So now for 4 indices, you will get the most simplest one, in which each index is connected by 2 lines. So we have 4 indices and 4 lines, so we can do square, and also these other ones that are related by permutations. And this turns out to be the most complicated coefficient to compute. Just this thing becomes very complicated to do in practice. And I'm going to close with this other coefficient. There are also other ways to put lines and connecting vertices. I just put 2 lines connecting the same 2 vertices and 2 lines connecting the same 2 vertices. And the sum of all these contributions can be organized here. So we will have 1, 2, 3, 4, 5 different terms contributing to the I4 with coefficients that can be computed explicitly in some non-trivial calculation, let's say. However, in the way that I've written so far, this formula doesn't satisfy clustering. That was one of the properties that I was mentioning at the beginning. The 4-point function factorizes, so it doesn't satisfy clustering. This 4-point function also factorizes. So we get a bunch of terms that are not that do not go to 0 when we separate regions far away from each other. However, we can reorganize the formula. Okay, these are just the way in which each coefficient is related to a graph of this type. Now we can reorganize each of these terms in a way that actually satisfy clustering. So this is one way to make sure that this contribution satisfy clustering, and also this term, and all the terms that are explicitly violate clustering, we put them together. So if the computations that we carry out are consistent, then what should happen is that the sum of all these coefficients have to vanish. This in particular means that not all these coefficients can be positive. This goes also in the sense that the I4, I3, etc. are not positive definite. And in reality, this happens to be the case. Once we do the explicit computation, we found that indeed this is 0. Something that we did not expect to find, that is, I think, nice, and maybe there is a general formula or general way to understand that, is that this expression, even though it satisfies clustering, can be further simplified. And indeed, it's simplified in this form, the form that I expressed to you before. And the reason is that the term that is linear in the 4-point function combines with the term that is quadratic in the 4-point function to get the connected correlator square. So this is just because this coefficient happens to be related to this coefficient. And in reality, there are three different coefficients for the general formula of the I4. So this is just to tell you that we can carry out the computations explicitly, and we get some nice formulas that satisfy the few properties that we know it should satisfy. Okay, so this is the general formula for the I4, and we end our analytic exploration ended at I4, just because this is kind of non-trivial to compute these coefficients. And what I'm going to tell you is that these formulas, we can check them against some numerics, at least for cases in which we can do lattice computations. And this case is precisely the case of free theories in 3 dimensions. But before, let me write down the general formula for free theories. For free theories, the 3-point functions vanishes. The 4-point functions by Wick's theorem reduces to products of 2-point functions. And so the general formula is just given in terms of 2-point functions. And the coefficients is, for the I2 and I3, we know it explicitly. And for the I4, we have a very complicated formula for this, which is written in terms of multiple integrals. We're not able to simplify those integrals. Okay. So, trying to check this formula in a particular number of dimensions, we go into the lattice and we do the computation in d = 3. The lattice computation that we did was using the Peschel formula, which just write down the entanglement entropy in terms of correlators of field operators in the reduced density matrix, or a conjugate momenta operator. So this thing is completely explicit, and you can put it in the computer. The type of geometries that we consider are geometries that were symmetric. So, and we were able to go even to higher parties entropy. So we went to I5 and I6. So this is the type of geometric configurations, like polygons of equal sized polygons, which are characterized by the radius of the spheres and the radius of the polygon, let's say. So the formulas of the lattice, we get some numbers for the I2, for the I3, for the I4, etc., which all those numbers happens to be positive. So maybe for free theories, you might be able to prove that this coefficient is always positive for the IN, for instance. At least for arbitrary dimensions and all the way to I4, we know it's positive from the general formulas that I presented to you. And the results that we got, the analytic results for that particular number of dimensions happens to match perfectly with this lattice computation. So for example, here you get it only up to the next significant feature, just a discrepancy. Although the I4 is not so accurate, but still is within 10% of error, let's say. Although I should say that this is getting this number is a little bit complicated because you have to evaluate multiple integrals numerically, not analytically. Okay, so this is just to check that the computations I have shown to you. It can be checked against some numerics. Finally, and here I might have to go very quickly because I would like to go through holography. Yes, so maybe I can just show you the answer for the coefficients. There is a way to do this OPE coefficient explicitly. So let me just go quickly. We have this formula that was introduced by Cassini, Testiantorova, and when you manipulate this formula a little bit and take the n going to 1 limit, then you end up having that this correlator in like an approximate expression for this correlator is just given by the 2-point function of the operator, where one of them has been modularly evolved by a certain parameter, a complex parameter or imaginary parameter. And this is why this, so this already gives us a very explicit formula for these coefficients for the piece operator. So what I would like to say is that because this involves the 2-point function of an operator and itself being modularly evolved, is that it turns out that these things becomes very simple for spheres, because for spheres, we know exactly how this correlator, what's the form of this correlator, because for spheres, the modular flow acts locally, and you can just write it down in terms of the ordinary 2-point function with a particular conformal factor. Yes, go ahead.
There's something that confuses me. That sigma tilde n looks like an integer, positive power of the density matrix. Right?
Yes.
So I'm kind of confused why it corresponds to a real-time modular flow, not Euclidean modular flow. I would have guessed that that's like sort of rotating you in the Euclidean plane by some angle. And I'm kind of surprised there's an I in your formula. It's like real time. Am I understanding this correctly? You're saying you're talking about
I
modular
think the formula I'm writing here is the modular flow. Yes, that will live in real time for real S. So it would be the opposite. So these formulas I'm writing you is for the Minkowski. I mean, the modular flow has support on the Kochel diamond. Is that right?
That's right. No,
the actual Lorentzian one. But when the formula that appears here is actually with an imaginary entry in the parameter S.
That's what.
So I guess would be the opposite. It would be like some kind of Euclidean version of this object. And that's what confuses you, the fact that I thought you were saying the opposite. That is.
Oh, sorry. So you're saying that. Oh, I see. So it's Euclidean modular flow.
Yes, it's Euclidean modular flow.
Oh, makes perfect sense. Yeah.
It's Euclidean modular flow. Yeah. I'm writing the formula for the Lorentzian one. Yes.
Yes.
I'm writing the formula for the Lorentzian. Yes. So this has this feature. But the nice thing is that then just using these formulas explicitly, you get a concrete formula for this coefficient. So it's a very explicit formula that now you can carry out all the sums that I told you at the beginning. You can carry out like super explicitly now. Of course, carrying the sums of products of these guys is also a non-trivial thing. But let me just show you one slide of what are the ingredients that you need to do, or the ingredients that these authors taught us to do. And essentially, just for 1 over the sine of this angle, you just need to use this integral representation of the 1 over the sine function that it's given in terms of some beta functions. And the advantage of using this is that the dependence on the angle just appear in the exponent of some exponential function. And then you can carry out the sums over these indices explicitly. And it turns out that it's also useful to introduce this integral representation for the beta function and so on. But then just by using these 2 techniques, you can carry out products of sums of these guys. I'm going to skip the example, but here I just quickly show you the example of the mutual information. So the mutual information, you just have the sum. You can carry out the sum explicitly, take the n-1 term, cancel, take it the limit, and then you end up with a double integral that you can carry out explicitly and get the function I told you before. So this is yet another way of getting to this number, to this function, using the framework that I'm describing for you today. Okay, so now the only thing that is left, I don't know if there are questions about this technical part, but the only part that is left, I don't know how much time could I spend on that? It would be to mention some things about holography.
Feel free to, how many more minutes you need?
Okay. So
is 10 minutes good?
Okay, yes, 10 minutes will be enough. Yes,
okay,
sure.
Thank you.
Okay. So in holography, first, I think we can make a prediction quickly just by using our free theory formulas. But just keeping the scaling dimension arbitrary, then I would like to say that the long distances, we have this prediction that the I2, I3, and I4 is positive for generalized free fields, just because of the computations we did explicitly. However, what I would like to do now, apart from this, I mean, this is just a prediction, let's say, what I would like to do now is how are these results consistent with the usual holographic way of computing entropies? So for that, we will need then the Ryutaka-Yanagi formula, or in reality, what we will need is the Faulkner, Lewkowycz, Maldacena formula, which involves this minimization, area minimization, but also includes the bulk entropy of the region in question. And the reason why we will also need to consider these bulk corrections is because in the regime that we are considering, the minimal surface of the union of regions is actually the union of the minimal surfaces, because you put the regions so far away that it just the minimization will just be the individual minimizations. And this immediately means that the area term will not play any role. Or in other words, that in particular, the mutual information associated to 2 regions in the boundary will be related directly to the mutual information of the bulk regions that are defined between the minimal surface and the boundary region. So this then if holography is consistent, I mean, in order to get results that are consistent with holography, we'd like to check that actually doing the computation in the boundary and the bulk give rise to the same expression. Let's say. So you can check this explicitly. This will be like a prediction of FLM, and what I would like to show you in the rest of the talk is that actually we can do it explicitly, not just for the mutual information, which was already done in this paper, but also for the N-partite information, because this going from here to here is trivial at the level of the FLM, but doing it explicitly is slightly different. Okay, So what do we do? What I would like to trace now is just a very simple parallel between all the computation that I described for you in the context of the CFT and the analogous computation that you will have to do in a QFT with some curve background. Many of the things that we did are independent of the curvature or the fact that you are in an arbitrary geometry. So, okay. So first of all, we have this twist expansion in the paper that we wrote here. We argue that actually, at least at leading order, just at long distances, like for the computation at very long distances, you can also do the same kind of OP arguments now with bulk fields instead of boundary CFT. Of course, I'm assuming that I can do this using also the replicate trig in the bulk. So we will get a similar expansion now in terms of bulk fields, and we have, in general, we have all different OP coefficients here, the same way than here. The formulas that I wrote to you, these formulas for the OP coefficients of the twist operator, are actually completely mimic in the case of the bulk. But now, of course, here it involves the inverse of the two-point function of the bulk field, of the bulk field, which is dual to this operator, so it's also a scalar. And you also need to consider this OP or this correlator. Now, the part that I skip over just because of lack of time, it also holds for the bulk field. It is independent of where we have a CFT or not. So in other words, the fact that you could argue that this correlator is actually related to the two-point function of a modularly evolved operator, this also holds for the bulk theory. It's also the two-point function of the bulk of the scalar field, in which one of them has been evolved, modularly evolved. And this is once again where the case of the sphere comes handy, because we know how to compute this correlator for the hemisphere, the boundary, the ADS hemisphere, which is dual to the spherical region in the CFT. So in both cases, we can write down explicit formulas. Okay, and that's the case because we know the modular flow action in the bulk theory, which is just a trivial generalization of the modular flow of the boundary CFT. They just need to add an extra coordinate in Poincare coordinates. Okay, so to finish the argument, let me analyze this formula in a little bit more detail. So, okay, sorry. Before that, okay, yes. Before that, this is just something I already told you, that the two-point function here, it is related to the two-point function of the operator being moved by the modular flow up to some conformal factor. But in the case of the bulk theory, what happens is that this transformation is actually just it's just a diffeomorphism. So the way the two-point function transform is just by the two-point function of the point being moved by the modular flow. There are no extra factors as it is in the CFT. This is the difference between these two correlators. And now let me describe a little bit more this site. So this part, here I just replaced the formula, clean it up a little bit better. And now let me work it out in more detail. So I put it here. Sorry for the many pieces. So this is the correlator I would like to study for you in more detail. So the ingredients are the two-point function, the bulk scalar. And we are considering this two-point function in the strict long distance regime. So we know that at long distances, this go like this. You have some powers of the C coordinate. And the two-point function of this scalar operator has also a similar expansion. It looks like it's essentially the same, but now with the coordinates being acted upon with the modular flow of the bulk theory. So we have these explicit formulas. And what I would like to tell you is that once we plug in all these formulas into this coefficient, what we get is that the bulk OP coefficient is actually related to the boundary OP coefficient by this very simple formula. So just recapping, the twist operator of the bulk region of the bulk theory for some bulk region has this expansion, as I told you. And the reason we keep this bilinear term in the bulk fields is because we want to compute correlators. So just to complete the argument, what now I need to tell you is that in computations of correlators of bulk fields that are far away, we can use the extrapolate dictionary to write it in terms of the boundary CFT, in terms of boundary CFT operators. So if we use then since this is the purpose of this approximation, then in this correlator we can use the bulk extrapolate dictionary to relate the bulk field operators in terms of boundary CFT operators. Using this fact and using this, then we end up concluding that the twist operator of the bulk region actually agrees at long distances with the twist operator of the boundary CFT operator, of the boundary CFT theory. So in conclusion, all these arguments that I hope they're more or less you were able to follow the arguments, but the conclusion is very simple, that if the twist operators agree at long distances and inside correlation functions, that means that the correlation function that we want to compute will also agree, and therefore the bulk N-partite information is actually identical to the boundary N-partite information. So, and this completes the things that I wanted to tell you about this story of the N-partite information. So just, I don't know if there are questions here, but then I will just end up with a quick summary. Yes, so the summary is that essentially I provide some formulas for the N-partite information in terms of twist operators. I describe a method, this diagrammatic method for computing the N-partite information, which can be made quite explicit in the case of the spheres. And then I presented some consistency checks against the lattice and holography as well by establishing this equality. Future work ahead of this is, of course, the question by Martin that how can we do this more explicit? Like how because it seems like we deviate a little bit. We start just computing some coefficients that some people might don't care about, but in order to actually have concrete formulas, we need those coefficients to actually be able to do the inversion problem explicitly. Second, I think the argument that I gave is so general that maybe it is not very hard to generalize it for arbitrary regions, not just for spheres. So we can argue that these two things are the same by explicit computation. And two questions that are more like open-minded is that I would like to understand better the mutual information in this mutual information expansion of Long and company, particularly in the context of holographic theories, because that might tell us something about the phase transition that occur from the mutual information. And then there remains the question of whether there is some similar bound, maybe not directly with the IN, but maybe with the absolute value of the IN with some particular combinations of INs, similar to the bound that presents the mutual informations. The mutual information put a bound on connected two-point functions, the square of connected two-point functions. So maybe the I3 also put some kind of bound on the connected three-point functions and so on. So trying to understand this N-partite information might give us some additional insight into the theory.
Sorry, can you remind me what's MA and MB?
Yes, those are operators that are defined completely inside the region A, and they are bounded.
But any operator inside B
Any
or
operator.
something?
Yes,
Okay,
it doesn't have to
you.
be local. It just have support. It just need to have support on the region A. Yes, any operator with support in A and B. Yes. Yes. So thank you, and please, I will try to answer any question.
Thank you so much for the wonderful talk. Are there any questions for Cesar? We had a lot of questions already.
Yeah. I went fast over many things, so I don't know if someone lose something that they wanted to lose.
I do have a quick question about your last comment about higher point functions. I'm a little confused about what you're looking for, because like MA itself could be a two-point function. So you have a bound of three-point functions. So, but you're looking for something else, right?
I mean, the point is that the I3 is not positively definite. Is that what you're saying?
Oh, you want a bound, you want the upper bound to be in terms of I3.
Yes, or in terms of something concrete. Yeah, yes. There's something, I don't know.
Yeah,
or maybe some combinations of I3 and I2 that will tell you something concrete about the or higher correlators, let's say. Because there is some kind of nice relation between higher correlators or higher N-partite information. So. And this parallel seems to be useful because we know that from correlation functions you can reconstruct the theory. So maybe that will give us some hint of how to go about this reconstruction program.
So you also mentioned that I3 is equal to 0 in free fermions in 2 dimensions.
Yes, yes.
Is this if and only if, meaning that it's the only theory?
It's the only theory that has this property, yes.
Known theory or provably the only theory?
Probably known theorem. I mean, if there is any other theory, it has to have the same mutual information. That's the thing, because the way that we prove, yeah. So I don't know if there is any other theory which has the mutual information of a free Fermi. Yes, I don't know if we can prove that. Yeah, that would be
Right.
good.
Any last questions for Cesar? If not, let's thank Cesar again for the wonderful talk.
Okay, thank you.
This was very, very clear. Thank you so much.
Oh, thanks a lot to all of you. Thanks for listening. And sorry for the extension.
No worries, no worries. Thanks so much. All right. Bye, guys.
Okay. Bye. See you.